Precalculus students, welcome to your 5.1 notes. Today we're going to take some of our knowledge of trigonometry and take the next step as we move forward and trying to understand all these relationships. On the first slide here, you're going to see several of the fundamental identities. Over here on the left, you can see the co-functions. We've talked about all of these. And then over to the right, the Pythagorean identities. The Pythagorean identities are going to take on an especially large importance as we go through this section. So you'll want to highlight these and make sure you understand all three. All right, so let's take a look at this. First of all, it says to simplify the expression. Now, there are lots of strategies you can take, but one strategy is let's try to change things into sines and cosines. So when I see tangent of x, we've already studied how tangent of x is the same as sine of x divided by cosine of x. And of course we know the cosecant is 1 divided by the sine of x. So if I look at this, sine of x over cosine of x times 1 over sine of x, you can see that we could cancel out the sine functions. We'd be left with 1 over the cosine, or debatably even simpler, we could just simply call that the secant of x. Okay, number 2. This time we're going to use a Pythagorean identity, and I know that this is the hint right here, cosine squared. When we see those, we got to start thinking Pythagorean identities. Now, one thing I can look at is if you go back to the Pythagorean identity that includes cosine squared, we could rewrite it to show that cosine squared theta is equal to 1 minus sine squared theta. Essentially just take the cosine squared theta plus sine squared theta equals 1, subtract cosine squared from each side. And that would be one way to rewrite this. So we could rewrite it as 1 minus, and then in parentheses 1 minus sine squared x. Some of you may have noticed there's arguably a little bit simpler way we could have approached this even. For now, I'm going to leave the cosecant of x alone. That simpler way would be to recognize that 1 minus cosine squared is just simply sine squared. Well, we're going to find that out here because 1 minus 1, those are gone, minus negative sine squared. So we've got sine squared x times cosecant of x. Now let's go ahead and simplify that cosecant. We know that cosecant is 1 over the sine. Sine squared is the same as saying sine of x times sine of x, so we can get rid of one of those and get rid of that, and finally we'd be left with our simplest answer, which is just simply the sine of x. Alright, another. This one, it looks a little scary perhaps when you first glance at it, but you realize, we've got these co-functions down. This is not a big deal to us. So sine of pi over 2 minus x, well, that's just cosine of x. And the cosecant of pi over 2 minus x, that's the secant of x. And then the one thing I have left to do on this particular problem is to see how I can simplify this. We know that secant is 1 over the cosine, so I'm going to rewrite it as secant of x divided by 1 over cosine of x. And of course, when we divide by a fraction, that's the same as multiplying by a reciprocal. So this is cosine of x times cosine of x over 1, or just simply cosine squared x. As we continue to the next slide, we're going to continue looking at simplifying various expressions. So let's start with this one, number 4, 1 over tangent squared theta plus 1. Now, if you've been paying attention, that denominator, tangent squared theta plus 1, should look familiar because it's one of our Pythagorean identities. 1 plus tangent squared theta is equal to secant squared theta. Now another thing we know is that secant squared is the reciprocal of cosine squared, right? And 1 divided by 1 over cosine squared theta would be exactly cosine squared theta. And I would say that would be the simplest form for that problem. All right, number 5. Hey, you guys have seen these. Cofunctions. The cotangent of pi over 2 minus x, that's the tangent of x. The tangent of pi over 2 minus x, that's the cotangent of x. Now there are a few ways to think about this. If you understand this relationship, you'll know. If you want to change to sines and cosines, it would look like this: sine of x over cosine of x times the cosine of x over the sine of x. And what do you know? We're left with exactly 1. The sines cancel, the cosines cancel. We're left with just the lonely number 1. All right, why don't you pause the video, give number 6 a shot on your own, and then we'll come back and I'll walk you through what I did. All right, welcome back. So let me show you what's going on here. This is the approach I took to it. I knew that secant was 1 over cosine and cosecant was 1 over sine. That was my first adjustment. And that gave me sine over cosine of theta plus cosine theta over sine theta. And now to go from this step to here, what I did, I'm talking about this step right there, I needed a common denominator. The common denominator was sine of theta times cosine theta. So I had to multiply the first term by sine theta over sine theta. We're talking about this one here. This term had to be multiplied by cosine theta over cosine theta. Now the nice thing about this was it gave us a sine squared theta plus a cosine squared theta, and hopefully you're recognizing, hey, sine squared theta plus cosine squared theta, I've heard that, that's exactly 1. Now, I think there's an argument that 1 over cosine theta sine theta would be a reasonable answer. If I can get rid of fractions, I do and use the reciprocal functions, but really either of these answers down here are fine. All right, let's continue on. This time the instructions say to factor and simplify. So let's do that. And I notice on number 7 that I can factor out a sine squared, and this is phi, by the way, and some of you may call it phi. It's one of those Greek letters. This one can be pronounced either way correctly. So sine squared theta times cosecant squared theta minus 1. Now here's the thing. If you look back at those Pythagorean identities, we have one that says 1 plus cotangent squared theta equals cosecant squared theta. If you rewrite it, you'd get cosecant squared theta minus 1 equals cotangent squared. Now this isn't theta, this is phi, but the good news is we can just change this to a cotangent squared. Again, those Pythagorean identities carry a lot of weight here. They're really important for you to know. And now at this point, it's like, okay, well, I need to keep simplifying. So what I would do is change everything into sines and cosines. This is a pretty common theme. Anytime you have something that's not a sine of theta or a cosine theta, you have an option of changing it there. All of them can be changed pretty easily. And then the other thing that we tend to look at a lot would be, of course, the Pythagorean identities. So those two things come into play. And look at that. All I'm left with is a cosine squared phi. All right, on number 8, this is an alpha Greek letter. So sine squared alpha minus 9 over sine of alpha plus 3. Now, I might be tempted to use a Pythagorean identity because I see this sine squared. But truthfully on this one, I think we have a much better option here. Sine of alpha minus 3 times sine of alpha plus 3. Anytime you have a factorable term, you want to consider that possibility as well. So it's a little bit different approach than what we've done on some of the others. But I think you might recognize it because of the denominator, like, hey, this I can find that up there too. And when you look at that, that term is gone, and we are left with the sine of alpha minus 3. And there's really nothing else we can do with that. All right, moving on to number 9. And this weird looking W shape, by the way, is an omega. Just FYI. Throwing plenty of Greek at you today. So we're going to factor and simplify. Now, if you're comfortable with using the trig and seeing these exponents like 2 and 4, you might recognize this right away and say, hey, this is 1 minus cosine squared omega times 1 minus cosine squared omega, which would just be 1 minus cosine squared omega squared. Okay, and then hopefully you're seeing, hey, 1 minus sine squared, or excuse me, 1 minus cosine squared. I've seen that before. That's sine squared omega. And that's just coming from that basic Pythagorean identity, sine squared theta plus cosine squared theta equals 1. This is the rewritten version of that. 1 minus cosine squared equals sine squared. And anytime you take something like a sine squared and you squared it, that just means sine times sine times sine times sine. So this is sine to the fourth omega. The Greeks would be upset with my letter drawing capabilities. All right, sine to the fourth omega. By the way, let me show you an alternate way on that one, because some of you this may bother you to have all these trig functions going on. So I'm going to use what's called a substitution method. You can do this if you'd like. There's no reason you'd have to if you're comfortable with what I've done up here. But some of you may not like all the trig and the fourth degree and the second degree. So you could do a substitution on this one, and you could say something like u is the same as cosine squared omega. Okay, and then we can rewrite it and say 1 minus 2 cosine squared omega would be like saying 1 minus 2u. And then cosine to the fourth, that's cosine squared squared, so we could just do plus u squared. And then it might be easier for you at this point, you can say, oh, well, that's just 1 minus u quantity squared. And then at this point, we'd want to go ahead and plug in. We said u is cosine squared, so let's plug that back in now. And it'll take us right back to what we found the first time. I'm going to skip a step here and just go to sine to the fourth. You can see the rest of the work right up above. And again, for some of you, this is not helpful at all. But for some, it's easier to factor when you can get those trig functions out of the way. Now, I would suggest on the next one, though, looking at 10 now, we really kind of have to factor with what we have. We can make this real ugly by trying to change secants into cosines and tangents into sines and cosines, and you might find a pathway that would work. It should be fine. But I think there's a better option here, and that is you've got a fourth degree minus a fourth degree. Let's change it to a difference of perfect squares. So secant squared x minus tangent squared x times secant squared x plus tangent squared x. Now, again, if you think back, we have a Pythagorean identity that says 1 plus tangent squared theta equals secant squared theta. Seen that one a few times today, and we'll see it some more. But here's the deal. If I rewrote that, I could rewrite it as secant squared theta minus tangent squared theta equals 1. So secant squared x minus tangent squared x, well, that's 1. That's convenient. And you know what else I could do? I mean, look at this. It says right here, secant squared is 1 plus tangent squared. So what if I rewrite that secant squared as 1 plus tangent squared x, and I still have that other tangent squared x over here, and all of a sudden it became, well, marginally simpler. We're down to one trig function, so in that respect it's simpler, and it's also simpler in the respect that we have a second degree rather than a fourth degree. But there's really not much else we could do with that. We can't change this to a secant squared. It's 1 plus 2 tangent squared, not 1 plus tangent squared. So we are done with number 10. All right, we only have 3 questions left. They're all just little variations of things that I mean, honestly, we kind of have the skills to do them, but they just look a little different, so we wanted to make sure you had a little practice. So here we're going to use trigonometric substitution to write the algebraic expression as a trig expression of theta. And you notice it says with 0 less than equal to theta less than equal to pi over 2. The translation there is quadrant 1. We like quadrant 1. Everything's positive. All right, so let's be happy, stay positive, and stay in quadrant 1. Let's just plug in for x a 3 tangent of theta. So we'll have 3 tangent of theta quantities squared plus 9. Of course, that whole thing is inside that radical symbol. All right, now I'm going to start doing a little simplification work. I'm going to apply that square to both the 3 and the tangent of theta, so I can rewrite this as 3 times 3 is not 3, is it? 9 tangent squared theta plus 9. And I can keep going with this. Hey, why don't we factor out a 9 from inside that radical and make it 9 times tangent squared theta plus 1. Wait a minute, we've seen this tangent squared theta plus 1 thing somewhere else. We saw it as a Pythagorean identity. 1 plus tangent squared theta equals secant squared theta. Now here's the key to that step right there. There is no more addition. It's only multiplication. So now I can apply that radical. We know the square root of 9 is 3. We know the square root of secant squared is secant of theta, and we cannot get it any simpler than that. All right, let's take a look at number 12 then. So on number 12, we're doing the same thing essentially, trig substitution. Now this time it's an equation, not just an expression. And note the change in quadrants. It's negative pi over 2 to pi over 2. So that's like our range for the arc sine and arc tangent is basically what we're talking about. And they added in one extra thing just to mess us up a little bit, find sine theta and cosine theta. All right, so here we go. What I'm going to do is start with the substitution. 2.5 is equal to 25 minus, and I'm going to go ahead and square this because you guys are pretty advanced. I think you could square 5 sine theta at the same time you plug it in. And of course, you're probably saying, hey, put that square root there. All right, deal, we'll do that. Now, there's some interesting options we have here. It might be tempting to try to undo the square. I'm going to suggest not to do that. Instead, follow along with me here. Let's factor within that radical. We'll have 25 times 1 minus sine squared theta. This 1 minus sine squared theta is the kind of thing we're looking for, because now look at this. 2.5 is equal to, well, that's the square root of 25 cosine squared theta. I'm going to transfer my work up here, and the nice thing about that is we again no longer have any addition or subtraction, so I can rewrite this and apply the radical. So the square root of 25 is 5. The square root of cosine squared is cosine theta. We know how to solve. Divide both sides by 5. Cosine theta is 2.5 divided by 5. That would be 1/2. Since we know the cosine of theta is 1/2, we basically know where we are on the unit circle. Normally we would say, okay, so if cosine theta is 1/2, that happens at 60 degrees, or pi over 3 radians, and in that case the sine of theta then would be square root of 3 over 2. Now I have to point out there's one kind of strange thing here. There's another place where cosine theta is equal to 1/2. It happens to be at negative pi over 3. And you'll note that at negative pi over 3, the value of the sine function changes to be negative. So this might be a little picky, but technically our sine theta could be a positive or a negative in this particular case. All right, our final one. Oh, look at this. Trig, absolute value, and logarithms all in one problem. This is what we math teachers love, and I think you will too. It's really not that bad of a problem if you think about it. If you know your properties of logarithms, you know when you have subtraction here, it leads to division. So the natural log of the absolute value of the tangent of x divided by sine of x. By the way, just a quick note, the absolute value bars. The reason those are there is because if you think back to what we know about logarithms, you'll know we cannot take a log of any base. In this case it's base e, but really it doesn't even matter what base, but you can't take the logarithm of a negative number. So we have to have those absolute value bars there because we know that at times tangent values or sine values could be negative, but not today. All right, so here we go, the natural log of, well, I'm going to rewrite tangent of x as sine of x over cosine of x, and that whole thing is divided by sine of x. And we know that sine of x divided by cosine of x all over sine of x would be the same as the natural log of 1 over the cosine of x. And I would argue that's a pretty good answer. I actually think I like this one just slightly better. Let's use that reciprocal function, the natural log of the absolute value of the secant of x. Hey, I know this lesson might be a little bit challenging at times, and it went a little longer even than I wanted to on the video, but I think it's good stuff. It's good practice, and it'll help you as we try to improve our understandings of trig ratios. Have a lovely day.